Behold the mesmerizing phenomenon of Death Valley's sailing stones, which have inspired Virginia Tech engineers to create an innovative ice slingshot capable of propelling frozen water discs across a flat, grooved surface without any external force. This breakthrough, reminiscent of the mysterious stone movements in Death Valley, showcases a forceless propulsion technique that differs from previous experiments involving dry ice on a vapor layer. Remarkably, the ice slingshot achieves this motion without emitting harmful CO2. Drawing upon the concept of Laplace pressure, the Virginia Tech team, led by Associate Professor Jonathan Barreco, has developed a mechanism that could pave the way for energy generation devices, micro-transportation systems, and efficient de-icing methods. Their approach, dubbed the Laplace slingshot, leverages the unique properties of ice and surface geometry to create self-propulsion, a concept that could potentially revolutionize various industries. For those unfamiliar with Laplace pressure, it's a scientific principle that explains how droplets of water can levitate on a cushion of their own vapor when deposited on a superheated surface. This phenomenon, known as the Leidenfrost effect, has been observed in previous studies where droplets self-propel across asymmetric sawtooth structures. The ice slingshot takes this a step further by utilizing simple geometric patterns such as V-shaped or herringbone grooves to induce self-propulsion without the need for superheated surfaces. But here's where it gets intriguing. The team's inspiration stems from the enigma of Racetrack Playa in Death Valley, where boulders have been observed to move across the desert floor without any apparent cause. This mystery has puzzled scientists for years, with various theories proposed to explain the stone's movements. However, recent video evidence and scientific analysis have revealed that the boulders are lifted by thin sheets of ice, formed from water that resists seeping into the desert's hard surface, and are transported over distances of 10 to 100 meters at speeds of 2 to 5 meters per minute. Building upon this understanding, the Virginia Tech team sought to replicate the self-propulsion effect with ice sheets on a grooved surface. In their initial tests, ice discs placed on a featureless, smooth surface lacked directionality and merely floated on their melting ice. However, when the team etched the surface with grooves in a herringbone pattern, the ice discs exhibited self-propulsion. The meltwater beneath the ice discs flowed along the surface channels, carrying the ice disc with it in a manner akin to tubing on a river, but driven by the directional channels rather than gravity. To further explore the possibilities, the team applied a super hydrophobic coating to the etched aluminum surface. Contrary to expectations, the coating initially anchored the ice discs in place due to the increased speed of the meltwater. However, after sufficient time allowed for the meltwater to accumulate in front of the ice disc, the resulting difference in Laplace pressure suddenly slingshotted the ice across the surface at a speed comparable to that of Leidenfrost ratchets. This pause and release mechanism earned the device the name ice slingshot. The potential applications of the ice slingshot technology are vast and promising. Professor Barreco envisions energy generation devices that could harness the small but measurable force to produce electricity, replacing the use of expensive and toxic CO2 with water. While the energy output may be less than that of CO2-based devices, the cost-effectiveness and environmental benefits make this a compelling alternative. Another area ripe for innovation is de-icing of surfaces, such as airplane wings, windows, and buildings. By growing frost on super hydrophobic grooves and utilizing Laplace pressure to slingshot it off the surface once partially melted, the team aims to significantly enhance the speed and energy efficiency of defrosting processes. The Virginia Tech team's groundbreaking research, documented in the study Self-Propelled Ice on Herringbones, published in ACS Applied Materials Interfaces, opens up new avenues for exploration and practical application in various fields. The simplicity and effectiveness of the ice slingshot mechanism could lead to cheaper and more sustainable solutions for energy generation and de-icing, marking a significant step forward in technological advancement. What do you think about the ice slingshot's potential applications? Do you see any other areas where this technology could be beneficial? Share your thoughts in the comments below.